this video, what we are going to do is, as I said in the last video, we are going to draw logic circuits, yeah, obviously circuit diagrams, but only using NAND gates. Okay, so let's put it as NAND gate. Okay, put it as NAND gate. So what do I mean by only using NAND gates without using other gates? Well, due to the complexity increasing throughout the course of evolution of computers and how we work with logic circuits, we can't just prepare, different types of gates like AND gates, NOT gates, and etc. etc. because that will make the production cost high, obviously. So the scientists had to come up with a way so that they create a single gate that can be used in multiple ways to come up with other gates also. Okay, and NAND gates and NOR gates perform the universal gate system. Okay, so they can be used to create any type of gate, you can use it to create OR gate, you can create it use it to create AND gate, or even you can use it to create NOT gate by using NAND gates. That's the idea. Okay, so that's why NAND gate and NOR gates are called as universal gates, and we will be learning about NOR gates in the next video, but for now let's focus on NAND gate. Okay, so first of all, let's talk how we can come up with the NOT gate. Okay, how we can come up with the NOT gate, because that's very important when we are studying. Okay, so we know if we have something like A, if it is passed through a NOT gate, okay, the output will be A bar. Okay, so the required output here is A bar. That's what we need. Clear? So that's what we are going to do using NAND gate. Okay, so what we are going to do is we are going to pass A in two signals. Okay, we are going to pass A as two signals into a single NAND gate. Okay, into a single NAND gate. So if you look at this closely, okay, I'll just tell you how it works. So let's talk about the signals. So first of all, the input signals are A and A. That's what we have here. Okay, A and A. So if you are passing A and A, the output will be A dot A whole thing bar. So the output will be A dot A whole thing bar. Let's say that is equals to F. Well, then we can say F is equals to A dot A whole thing bar, and we know according to the idempotent law, A dot A is equals to A. So A dot A whole thing bar can be given as A bar. Okay, so here the NAND gate, is working like a NOT gate. Okay, here the NAND gate is working like a NOT gate. This is all you have to do. What you have to do is you just have to send two or more signals of the same variable. Okay, just make it two or more. Then the output will be NOT gate. Okay, so this is how NAND gate acts as a NOT gate. This is how NAND gate acts as a NOT gate. Now let's talk about AND gate. How we can work with AND gate. How can we create an AND gate by using NAND gate? So we know in an AND gate, when we pass through two signals A and B, okay, the output should be A dot B. Okay, the output should be A dot B. Okay, that's what we are looking for. The desired output is A dot B. How can we do that with NAND gate? That's the idea. Clear? So it's also simple. Okay, we need A dot B. Okay, so if you remember in the last video I taught you, we can double negate things. We can double negate things. If you remember that clearly, I taught you double complementary to rearrange the expression. Okay, that's what we are to A dot B whole thing double bar. We can write it like that because double bar is equals to actually the same thing. Okay, because that's what the double complementary law tells us. So A dot B whole thing double bar. Okay, that's what we have. A dot B whole thing double bar. Now I am going to do. Okay, now what I'm going to do is, so since here we have a NAND gate. Okay, here we have a NAND gate, and we just need a bar, extra bar or a NOT gate. I can combine these two ideas to find AND gate. Okay, so I hope you understand the thing. What I'm trying to say is, if A dot B, okay, if A dot B can be given as A dot B whole thing bar, okay, A dot B whole thing bar, whole thing bar. So here I just have to use a NAND gate. Here I just have to use a NAND gate. Here, what I have to use is a NOT gate. Okay, so if I pass A and B through a NAND gate, then through a NOT gate, we can actually come up with the AND gate. Okay, so that's what we are going to do. So we have A, we have B, we are passing it through a NAND gate first. Okay, we are passing it through a NAND gate first. So which will give us A dot B whole thing bar. Now what I have to do is I just have to pass them through a NOT gate. But we can't use NOT gate directly here. Why? We are only using NAND gates. So as we already studied, if we pass the same signal twice or more through the same NAND gate, we will get the output of negation. So this will give us A dot B whole thing bar, which is actually equals to A dot B, yeah, A dot B. That's it. Okay, so here we have A dot B whole thing bar coming. Here also we have A dot B whole thing bar coming. And when we send it through an AND gate, we get A dot B whole thing bar into A dot B whole thing bar, whole thing bar. And we know according to the idempotent law, this reduces into A dot B whole thing bar, whole thing bar. And we can remove the double bar. Why? That's what the double complement law suggests in Boolean algebra or Boolean law. Okay, so this is how you have to create an AND gate. Very simple. You just pass the signal through a NAND gate, and then it is passed through a NOT gate that is created by using an AND gate. That's it. Okay, for AND gates, you need two gates. For AND gate, you need two NAND gates to create an AND gate. Okay, that's it. Now we will talk about OR gates. Okay, in OR gate, we know the logic. If A and B are sent through an OR gate, we know the output is A plus B. Okay, so we are expecting the desired output is A plus B. I can rewrite this as A plus B whole thing double bar. And I can break a single bar. Why? I can break this bar, this specific bar, including this. So that will give me A bar dot B bar. Okay, so you know, right, De Morgan's law. A plus B whole thing bar can be given as A bar dot B bar. We have another bar whole thing this expression. So holding this expression. So we have to put that also. That's it. So now, if you see clearly, okay, if you see clearly, we have a NOT gate for A here, we have a NOT gate for B here, and then those signals are passed through another NAND gate. Okay, those two are passed through another NAND gate. So that's what we are going to do. So first of all, let's create A bar. So that we need a NOT gate, and we are creating it using a NAND gate. And similarly for B also, we need a NOT gate. So we are creating it by using a NAND gate. Now we can pass them through another NAND gate, okay, and the output will be equals to OR gate. Okay, the output will be equivalent to OR gate. So we have A here, A here, A here, and since this is acting as a NOT gate, it will be A bar. Similarly, B here and B here. This is B bar, and here we have A bar and B bar. So the output will be A bar dot B bar whole thing bar. Okay, so if I break it, F can be broken down. A bar dot B bar whole thing bar. If I break it, I will get A double bar plus B double bar, and the output will be A plus B. That's it. Have A plus B. Okay, so I hope you understand this. Okay, I hope you understand this.
Thanks for watching the 21st video in our Logic Gate series. If you found this guide to building NOT and OR gates using only NAND gates helpful, don't forget to like, share and subscribe for more lessons. Hit the bell icon to stay updated with our latest videos, check out the full playlist to master Logic Gates, and follow us on Instagram. I will see you in the next video. Until then, keep learning and stay curious. Bye bye.